So, to end this off, we've got our choice of base. So one of the last things that we tried to finish up but didn't quite get to was our chapter 10. Chapter 10? I think it was chapter 10. And looking at our enolates, and in particular what was special about them. So the whole point was taking a carbonyl compound and converting it across to the enolate. The special aspect of our enolate is that we now have a negatively charged carbon, which means we have a carbon nucleophile. Carbon nucleophiles are not easy to make, and in fact, we spend a significant portion of time talking about carbon nucleophiles and how difficult they are to make because of that. So they're extremely synthetically useful because we can go through and expand our carbon skeleton by generating these nucleophiles. But the question is, how do we go through and make them? So very clearly we need a base. We're starting with a carbonyl. Okay, that carbonyl has chemistry centered on the oxygen, being potentially nucleophilic or basic. Okay, but we want the carbon to be basic, so that's a bit more nucleophilic. The carbon of our carbonyl is rather electrophilic because of that polar pi bond, and that's what we'll talk about when we move into chapter 17. But then we're kind of shot down on the carbonyl until we move out to that next position. That carbon is referred to as the alpha carbon. It is the first carbon after the functional group. The functional group is the carbonyl. So our first carbon after is our alpha carbon. That carbon can be deprotonated. And that's what we're showing in all three of these reactions. We remove that hydrogen and put a negative charge on our carbon. And we might immediately say that is a horrible thing to do. Why would that be a horrible thing to do? We would say carbon's a horrible carrier of that charge. We're looking at a very non-polar bond between the carbon and the hydrogen. We'd say there's no way that that hydrogen is acidic because the negative charge on that carbon can't stabilize it. Okay. And if we move to Gen Chem, we'd all probably, or not Gen Chem, first semester we'd all probably say, oh, that's not very acidic. Okay. But if we now add our further information, remember that we also have this little deal going on, which happens to be, hearing somebody mouth it, resonance. Which of these structures is more correct? Neither. They're resonance structures. They're identical. Okay? So both of these are involved in understanding the reactivity of this structure. Why does this become important? Where's our negative charge held now? On an oxygen. Can oxygen hold a negative charge? Yes. That hydrogen does become acidic due to this resonance contribution. It's that resonance that allows us to have this reactivity. Is this something that we probably predicted? Probably not. More than likely what happened is someone added a base, expected some other reaction to occur, and it didn't occur, and they got some weird result. They analyzed that weird result, and this is what they found. Right? This wasn't someone just staring at it saying, oh, this must be the case. Okay? So, but what base do we use? So you'll notice I've given you three choices of base here. First one's probably the most common, but we could have used something like hydroxide, roughly equivalent. In the next one we've used hydride, and in the last one we've used something known as LDA. L for lithium, which nicely isn't shown in this case. D for diisopropyl. And A, amide. So the lithium's not shown, but when we take a look at those carbon groups, how many carbons are they? 3 carbons in each of those substituents. There's our propyl. Why is it iso? Because it's connected to the nitrogen through that center carbon. So we have diisopropyl amide. Right? 3 different bases. Which base should we use? Well, does it matter? Any guesses? Does it matter what base we use? Yes, it does matter. Okay? And we even have that information included for us on this slide. Where's that information hidden? If we take a look at our arrows, you'll notice for the last 2, which way does our reaction go? It goes towards our products, forming the enolate. Not only that, it's also irreversible. Those last 2 only form the enolate. They do not form any of the carbonyl or stay at the carbonyl. Whereas if we started with the hydroxide, our negatively charged oxygen, most of that reaction doesn't occur. We end up with a very small concentration of the enolate. Why is this important? Well, it depends on what you're trying to do. In the case of Chapter 10, we were trying to make a nucleophile. Okay? We wanted a nucleophile so we could do our substitution reactions. Which of these would be a horrible choice for Chapter 10 chemistry? The top one. It doesn't form the carbon nucleophile. If it doesn't form the carbon nucleophile, we don't do the substitution, the whole reaction shuts down. Okay, so depending on what we're trying to do, we may select a variety of different bases. Okay? Next part of this is trying to decide what's going on with this irreversibility. Okay. Why are the last 2 irreversible? So let's pick the easy one. Yeah. And that middle one, we produce H2 gas. To do the reverse reaction, what do I need to have present? I have to have that hydrogen, right? If I form H2 gas, where does that H2 go? Is there any hydrogen present? No. What does that mean? You physically cannot do the reverse reaction. So that one's a pretty awesome reagent. However, what's the issue that comes with this? It's the same, it's a good thing and a bad thing. We end up forming H2 gas. What's the issue with H2 gas? It's incredibly flammable, and we're already in an organic environment where everything is already flammable. By adding an even more flammable thing into it, our whole experiment could go up in flames. So producing hydrogen gas could be a bit questionable as a choice. What about the other 2? Just because it's bulkier isn't going to prevent the reverse reaction. Not a bad idea to look at size, but didn't quite work out for us. Could start to evaluate where our charges are held. Okay. The nitrogen can hold that charge better than the carbon and oxygen, so maybe that, the nitrogen can't hold that charge very well. Whereas when we look at our final product, we're putting that negative charge across a carbon and an oxygen. Which can hold the charge better? The carbon and oxygen we end up forming towards our final products. Okay? So there's that difference in electronegativity on that nitrogen. When we go up to the top reaction, why might that one be reversible? What atom's holding the charge? Oxygen or oxygen. Which one holds a charge better, oxygen or oxygen? It's the same, which means we're looking at roughly an equilibrium reaction. There is no real strong favoring one direction or another. Okay. Last way we could do this, which is kind of a cheaty method, we could evaluate our pKa's. Okay. It's a cheaty method because really what we're saying is we go into the lab, find out what the answer is, and then say that's the answer. Okay. It's true, but it's kind of a backwards way of doing it. The pKa for our carbonyl compound, It's roughly a 16. pKa for ethanol, roughly 16. Okay. It's actually a little bit lower than that. I think it sits at like 15.5. Given that information, which way does our equilibrium favor? Reactions all favor the weaker acid. The weaker acid has the higher pKa. Our reaction favors the left. No enolate. What happens when we drop down to the last one? We're still looking at a pKa of roughly 16, and we're now going to compare that to the pKa of the amine, which is somewhere at 30. Okay. Which side of the reaction is favored? The right. How much is it favored in comparison to the first one? Well, in the first one, it was almost perfectly at equilibrium, so there's virtually zero favoring. In the last one, remember, we're on a logarithmic scale. If we go up by 15 units, what is that? 1,500 times favors the right. Did I do that right? Anybody know your logarithmic scales well enough? Okay, we'll take that as a no. It's a really big amount favoring. Is that it?
I think it's like 10 times for each.
I never.
It's
15 orders of magnitude, so that's 1,500, isn't it? Okay, it's a lot. 150. It's a lot favoring the product. Okay, so much so that what does that mean about the reverse reaction? It doesn't happen. Okay? So by changing the base, we can change how much enolate we form, which then changes what we can then do with it. If we have primarily the enolate, we now have a strong nucleophile. We can do a lot of chemistry with it. If we have a very small amount of the enolate, that's going to change our overall chemistry because now we have less of a concentration of that nucleophile. That's going to change how we can approach a question. Okay? Ultimately, in all cases, what are we doing? Removing a hydrogen. That's it. There are some pKa's. Oh, I was slightly off. I was pretty close there. How do we get hydride? Talked about this briefly in lab. How do we get just H minus? So we could try borohydride. Borohydride does not work very well under this circumstance. The borohydride gives us a hydride nucleophile. What do we want the hydride to do in this case? Act as a base. So borohydride is not the best option. What we can add instead is sodium in front of it, sodium hydride. So here's an interesting question. Is that a big base or a small base? Interestingly enough, that is a massive base. It's one of the biggest bases we have. We'll talk about why in a little bit. Okay. Choice of our enolate. What happens if we have an unsymmetric or an asymmetric ketone? So if we go through and take a look at this, we've got two locations that we could possibly remove the hydrogen from. Depending on which hydrogen we remove, we end up changing the carbon that's nucleophilic, which means we're going to change the end result we get. So we have to know which one is going to be favored under which conditions. So to approach this, really what we end up with is a thermodynamic and a kinetic situation, as we've seen before. You think you guys can solve this on your own? Give you 5, 4, 3, 2. We're going to take that as a yes. So what was wrong with that drawing? Whoops, as I record. What's wrong with this? How many steps are shown with this energy diagram? One step. If we look at our reaction, how many steps? 2. Right? So we've got a problem there. We have to fix that. So, blue versus red. Why did I draw the blue? And I'll even add an extra label down here, products. Why is my blue product lower in energy than my red product? What we're going to do is look at our products and say, what's the highest energy thing there? Well, the highest energy thing there is the pi bond because we're using p orbitals. Which pi bond is lower in energy? The more substituted one, which was generated from the blue hydrogen. So our blue product ends up being lower in energy than our red product. The next part then transfers across to our transition state and what's happening within that. So we now look within that box. What's our our high energy thing in our transition state? The carbanion, that negatively charged carbon. Where's the negatively charged carbon more stable? On a secondary carbon or a tertiary carbon?
Tertiary.
Secondary is more stable. Okay. Why is a secondary more stable? Less electrons around it. You're thinking carbocations by saying a tertiary. Okay. A carbocation is more stable on a tertiary because it needs more electrons to stabilize the positive charge. A carbanion wants the opposite of that. It wants the least amount of electrons around it, otherwise there's too much concentration of charge. Which means our red product, or our red carbanion, is actually lower in energy than our blue. So when we look at our transition state, or our product, or intermediate, we end up drawing something along those lines. When we go through and connect, this is very similar in effect to what we had with the black lines over the top earlier that we said was wrong. Okay. Same general idea, but you're missing what an energy diagram shows. Okay. We now have our result. What's the difference between our red product and our blue product? One is thermodynamically favored and one is kinetically favored. Deciding that can be difficult. Okay. Thermodynamics has everything to do with reactant and product. We don't care about anything else. I don't care how I got to my products. I just know that I'm at products. Which means my thermodynamic product is going to be the one of the lowest energy, period. In a question where we're asking which is favored, the kinetic or the thermodynamic product, what does that mean the red one's going to be? Almost universally, it's going to have to be the kinetic product by process of elimination. There are reactions where the kinetic product and the thermodynamic product are the same. So don't rely on that too heavily, but in general, this works. To look at kinetics, we have to look at which happens first or faster, which means we're looking at the smallest activation barrier. So what happens if we have very low energy to run our reaction? Whichever one can get over that first activation hump first ends up being the product. There's my kinetic product. How can I ensure that I get the kinetic product in preference to the thermodynamic product? Make sure I have as low energy as possible. How can I make sure I have as low energy as possible? Keep it frigid. Okay. How can I ensure that I get primarily the thermodynamic product? Heat it up. Because if I add enough energy that I'm now over that activation barrier, it doesn't matter about speeds. All I want is my lowest energy product, and I can now clear and make it to the thermodynamic. Kind of makes sense?
So would both of the products be lower energy than your reactants?
So deciding where the energy of your reactants, intermediates, and all that stuff are relative to each other. Compare your reactants to your products. And actually this one's probably a little bit weird. Our double bond should be a little bit higher up probably. Our enolate should probably be higher in energy than our reactants because we've added a double bond into the structure. Yeah, we added a carbon-carbon double bond into the structure. So that's probably going to elevate it over the carbonyl. Okay? So we should actually have that shifted higher. The intermediates, should they be higher or lower in energy than everything else? Higher because negatively charged. So the idea is that we just need to evaluate where all those species are relative to each other In general, our products tend to be lower in energy than our reactants because they're more stable. That's why the reaction ended up occurring. Right? In this case, we'd have to look at the other species to help drive that and get those lower, but those probably should have been drawn above the energy of our reactants. Okay. Questions? Okay. What happens if we bring in the choice of the enolate and a base? So we have an unsymmetric carbonyl and we use different strength bases. What ends up occurring? Okay. So let's say we use a small base versus a big base. What would we expect to happen? Which product? Our kinetic product or a thermodynamic product? For a small base. We had one answer so far. Why would a small base prefer the kinetic product? But it's a small base. Does it care about sterics? It's a small base. There is no steric concern, which means what product would we expect? Thermodynamic. If it's a big base, now sterics comes into play.
That's what you're saying. I thought you were saying small compared to big base.
Okay, so you're saying the same thing as now recorded? So if we move to a big base, we would expect which product? Our kinetic, because of sterics. The larger that base is, it's not going to be able to get into our sterically hindered thermodynamic hydrogen. Okay, and that's how we've addressed these questions before. What happens if we switch it up to a big, stronger base versus a big, strong base? Because in all these cases, we're using strong bases. So what's our big, stronger base? What's an example of our big, stronger base? LDA, our big, strong base. We'll come back to NaH, but that is not a bad idea. Could use our T-butoxide.
The stronger base we've been looking on that because it's more favoring the product.
What ends up happening when we go through and evaluate these? Okay. It's now no longer a steric argument. We have to look at the stability of everything else involved, including our bases, and ultimately the reversibility of each of those reactions. Is LDA reversible? No. Is the T-butoxide reversible? Yes. Okay, that was looking at our bases. That reversibility changes how our bases react with those individual species. That's why we have that energy diagram, which I don't know why I'm going back to because it's no longer there. Okay. We're looking at how we shift around on those dynamic curves. It's what our energy diagram does for us. So what ends up happening? If we use LDA, it ends up forming our kinetic product. It happens wickedly fast. Okay? So in all cases, what we're evaluating is our kinetic versus our thermodynamic. Kinetic is always going to happen fastest because it's kinetic. Okay? It will always happen the fastest. LDA goes through and reacts with it, but is LDA reversible? No. So what happens? I form the final product and that's it. I've got my kinetic product. What happens when I add the T-butoxide? I'm having a hard time spelling that. The kinetic product still forms first. But what's the issue with our T-butoxide? It's reversible, and it goes back to forming our starting material. Then what can happen? Some of it goes through along the thermodynamic path. What happens when I get the thermodynamic product? It can't go back anymore. It is the now lowest energy possible. Which means the thermodynamic product now sucks everything out. What happens with the equilibrium? My kinetic product that I may have initially formed with the T-butoxide, now according to Le Chatelier's principle, reverses all the way back down and around to our thermodynamic product. Okay? So it has to do with the reversibility of each of those reactions and the energy diagram of our different enolates. So when we add LDA, we get the kinetic product, which means our carbon nucleophile is the least substituted nucleophile. If we use T-butoxide, okay, we have the most substituted nucleophile. Was this on the exam? Yes. It was also made extra credit. I think it was one of those last three. I don't remember which one it was. All right? So we have to be careful with what base we're using because that's going to cause a different product to form. Ultimately, it's still the same thing. You are still removing a hydrogen. You're still generating that nucleophile. That nucleophile can then do some chemistry. The question is, what stage does that happen at? Questions on that? It's question 32. Okay. Sodium hydroxide. Or sorry, sodium hydride. Big or small base? Okay. I said it was really big. You all gave me this weird quizzical look. Why would you give me a weird quizzical look? Why is sodium hydroxide not big to you guys? Okay, it's hydride. It's hydrogen. That's as small as we can possibly get. Why is that so big? What kind of bond is there between sodium and hydride? Ionic bond. Okay. What part of sodium hydride is organic soluble? None of it is organic soluble. If we had switched to, say, butoxide, keep using the wrong eraser, we still have that ionic bond, but what part of it is now organic soluble? That T-butyl group. Why does that become important? Well, what happens when we try to do an organic reaction? We take our reagents and we put them into a solvent. That solvent happens to be organic. What happens when we take an organic compound or an organic solvent and put an inorganic material into it, like sodium hydride, that does not have any organic soluble parts? What do you mean by not much? Let's get more specific with it. You're right.
They don't really interact that way?
They don't interact, which means?
No reaction.
Not quite no reaction.
Slow reaction.
Take salt, add it to water, what happens? It dissolves. Take salt, add it to hexane, what happens? It's not nothing. It doesn't dissolve. What happens to sodium hydride when you add it to an organic solvent? It doesn't dissolve. Where's the only place that the sodium hydride can now react? On the surface. That is now sterically massive. Okay? We're only looking at a very tiny place where we can possibly see that reaction occurring. Sodium hydride is a large base, not because the molecule is large, but because the phase difference between where the reaction is occurring and where the sodium hydride exists are in different locations. You have a solid sodium hydride trying to react with a solution, for lack of a better word. That interaction space is so limited that sodium hydride actually acts as a massive base. Okay? It is a horrible nucleophile for that reason, because it is sterically massive. Really interesting observation, if you ask me. Questions?
I have a question real quick.
Yeah?
You said it reacts with the surface?
Only at the surface, yep. So the interface between the solid and your solution. It's the only place it can interact. So what do we end up doing once we've got these nucleophiles? Well, there's alpha halogenation. You can run under two different catalytic types. You can run under basic environment, or you can run under the acidic environment. When we went through to form the enolate, by definition, we went through and formed it under basic conditions. Because when you look at the enolate, what charge is it? Negative. An enolate is negative. So by definition, I need to be under basic conditions. But can I still form an enol? Yep, it's equally valid. But to go through and form that, it's no longer called an enolate because it is now not charged, and I have a hydrogen attached to it. Does the enol still have that nucleophilic characteristic? Yep. Just like with the base, I can push the electrons down onto that nucleophilic carbon, or I can do it with the enol. Same end result. The nucleophile is still happening at that carbon, but we're changing the mechanism and how it works. One of the big conclusions that comes out of this is that if we run under basic conditions, we force polysubstitution. So if I'm going to try to do this alpha halogenation, if I'm under basic conditions, I have no choice but to continue to put halogens instead of hydrogens at that alpha carbon. It will not stop. However, under acidic conditions, I can do it once. It's a neat little change. So why, under basic conditions, is it forced to continue to polysubstitute? Well, if we take a look at our starting material, after a single reaction, we substituted across and we now have our bromine. Okay. Why does this continue to react? But if I went under acidic conditions, there's still more hydrogens. If I go under basic, this continues. If I go under acidic, it stops. I'm not sure where you're going with that.
Hydrogen attached to the carbon isn't necessarily going to keep moving, well, not that it lets go of the hydrogen, but they're not going to keep getting picked off in an acidic solution because there's already a ton of hydrogens floating around, whereas in the basic, you're...
No, not quite. Interesting idea, but not quite. First step. What's the result? What happens? Form the enolate. First step in the next one, what happens? Form the enolate. What is special about that material that it continues to form the enolate under basic conditions? What type of reaction occurred in both those first steps? Say that again, Almadia. The first step. Acid-base. It was just a transfer of a hydrogen. What is special or different about our boxed structure in comparison to our starting material? What's that halogen doing? You're right. It is sucking electrons away from the carbon. The carbon is then losing electrons. So what does it do? Suck the electrons away from the hydrogen. We have an inductive effect, making our intermediate product more acidic than our starting material. Which means in our very first step where we reacted with a base, what happens? We make our first alpha halogen product, which is now more acidic than what we started with. So what happens? The base reacts with it first to do another substitution, which then makes our new product even more acidic, which then means It reacts again and again and again until we've removed all of those hydrogens. As soon as we put that halogen on, those hydrogens become more acidic. Under basic conditions, we can't stop that reaction because we've now made our intermediate more reactive than our starting material. Why does this not happen under acidic conditions? What's the first step? But under acidic conditions, we're not pulling off the hydrogen. Our first step is to neutralize that acid, which is protonate the oxygen. Whoops. Sorry, I have to figure out my arrows. We can draw a resonance structure. It is from this structure that we can then potentially remove that hydrogen. Why, when we put on a halogen, does this reaction slow? What can the halogen do? It can sort of stabilize that positive charge by having enough electron density that it actually prevents the next reaction. So we end up getting a mono substitution as opposed to a poly substitution. Nice little feature of that reaction. Let's fire it away, see what you guys can do. So we got the basic skeletons drawn up here. In that first reaction, it's kind of tricky because you got a lot of stuff going on there. PBr3 does what? What's that? For? Nope. Alcohol. Okay. Officially not alcohol, but for an OH. So good. You should be able to put the bromine on there. Okay. What's that Br2 doing then? It's our alpha halogenation. Are we running under acidic conditions or basic conditions? What functional group is that? Carboxylic acid. Acidic conditions or basic conditions? Acidic. So you do a single substitution at the alpha position, you have your bromine on there. That's step 1. What happens in step 2? Trickier, because we haven't talked about it yet. Usually you're looking at chapter 20 or 21.
Wouldn't water substitute, or the OH substitute?
The OH substitutes for the halogen at the end, and you end up with that as your product. Okay. Much, much trickier step. What I would expect you to be able to do is that first step, okay, for this reaction. Next one down, what happens? We're under acidic conditions and Br2, in the presence of our carbonyl. What does that start to suggest? Alpha halogenation. Draw on our bromine. Because it's under acidic conditions, we do end up expecting it to form primarily our more substituted nucleophile. We will get some of the other one as well, but this is our primary product. That's step 1. What does step 2 do? What was pyridine? So we saw it retaining stereochemistry because what did it do? That nitrogen acted as a mild nucleophile. How good of a nucleophile do you think that would be? It's a pretty bad one because it's how massive, right? So if it can't act as a nucleophile, what could it act as? A base. What happens? You do the elimination reaction. The pyridine acts as a base, removes the hydrogen, we kick out the leaving group. We now have a conjugated ketone with an alkene. I expect you to know that one or be able to predict that one. Yeah. You're starting to get to that point where you're looking at those reagents and saying, what can they do? What can they do? Okay. Why would we not expect pyridine to act as a nucleophile under that circumstance? It's massive, and where's our leaving group? Also in an equally massive location. The likelihood that we would be able to do the substitution of the pyridine for bromine, not very high, so the pyridine is going to have to act instead as a base. Last reaction, what happens? Same deal, alpha halogenation. That base pulls off hydrogens from our alpha carbon, which is only on the right-hand side, and we have a bromine. But since it's under basic conditions, we can't stop it. Okay. This was a fun little tricky one. What do we now have? A really good leaving group, which can be replaced by our OH minus coming in, kicking out our leaving group, and as an end result, when we put it all together, well, actually, that first step, we'd end up with this. We have a negative carbon, not particularly stable. Is there anything positive nearby? The hydrogen from our carboxylic acid. So at the end of step 1, we've got those two products. Step 2 does what? Adds our last hydrogen, and we've got our product. Where does this one commonly show up? That species, at the very end, happens to be relatively insoluble, particularly in an aqueous environment, which we're in with the sodium hydroxide. That insolubility causes a precipitate, and you see the formation of a precipitate. Very common ACS question. They'll take base, it's typically reacted with iodine, and then they'll say, okay, which of the following could be possible starting materials that would produce this product? Well, the only way it gets produced is if you have that methyl group so that you can form that leaving group. And that methyl has to be located at the alpha position of a carbonyl. So if you have a methyl ketone, that reaction occurs. Any other kind of ketone won't work. You don't get that precipitate to form. Also on the test. Extra layer of difficulty on the test. It involved nomenclature. You had to be able to name each of the starting materials. Okay? But all you were identifying was the methyl ketone. Don't look so depressed. How many of you biked in today? That's what I thought. Relax. It's not that bad. Could have been worse. This is not the best example, but let's go ahead and work through it. Looking at our syntheses. Try and include something like this every time. So we're starting with our methyl cyclopentene, and we want to somehow end up with that aldehyde structure. You are technically missing a reagent to do this reaction. Just because you don't know the reagent doesn't mean you can't start to work your way through. Okay? So, first step. What do you think we should do first? Is there any reactivity in our starting material? No. So that's probably a very good first step. Let's actually make it reactive. To make it reactive, what do we have to do? We're going to have to do a radical reaction, which does get rid of a hydrogen. And as Terry suggested last time, NBS is going to be our best bet. The result, we now have our bromine on our structure. Now we got something to potentially work with. Notice the carbon that is reactive. It is our tertiary carbon. If we look at our final product, the carbon that is reactive needs to be that methyl. So somehow or another, I have to move the reactivity out there. How can I get that carbon reactive? How can I move the chemistry out there? Did I miss something?
So what does it say below? The underside of your
H nu for light. Planck's constant times frequency. Frequency? Sure. How can I get the chemistry out to that other carbon?
Could you do like a hydride shift or something?
We could try a hydride shift, but if we did a hydride shift, that puts a positive charge on a primary carbon. That becomes problematic. What atoms are currently out on that carbon? Hydrogens. So ultimately, or officially, I'm going to have to, without any questions about this, I have to remove a hydrogen. Which means, what do I need to add? A base. So let's add a strong base. Let's just say strong base for the moment. So that might remove one of those hydrogens, but then I might have a negative charge out there. That's ugly, that's not stable. What could that strong base potentially do? Facilitate the elimination reaction to form that product. Anybody see any quick problems out of that? That is the least substituted double bond. How can I ensure that I get the least substituted double bond as my product? First semester.
Sterically hindered base?
Sterically hindered base, T-butoxide, or LDA. Either would work. Since we just talked about LDA, we could bring that in. The other option, which is a lot messier, but you could potentially go through and do it, is you could do your substitution with your NH3 and excess. We'll do your that gets problematic. But you could try and convert that into your large leaving group, doing your amine substitution to generate your Hoffman product. That's going to be a big, ugly mess. T-butoxide or LDA is going to be much more straightforward. We now have chemistry at 2 positions, one of those being our final product position. Cool. What's the other problem? We still have chemistry at that other carbon. What changes at that carbon versus our final carbon? It needs a hydrogen. Okay. What charge is that central carbon in our alkene? Partial positive. What's the problem with adding a hydrogen? That hydrogen had better come in as a negative charge. That's not particularly easy to do. Not only that, but what's happening at our top carbon? What needs to somehow eventually happen? I need to get an oxygen out there. Okay? Ideally, an oxygen double bond. Okay? Is there a reagent that allows me to add any one or multiple of these? Yes, there is a reagent. Involved in 2 steps. No. You'll very typically see it written in there. I'm not sure why they always show it there, but they do. That does our substitution of our H and our OH across the double bond in the anti-Zaitsev formation. How could we do that last step? This is the tricky one that you don't know the reagents for. What type of reactions occurring there?
Halogenation.
Good. Didn't think of that one. We have an elimination. How else could we reference it?
Oxidation.
It's an oxidation reaction. So you may not know the answer, but you know what's happening. If you know what's happening, you can process of eliminate your way through answer choices. Okay? Are you guys confident yet with synthesis? Not yet? No? Okay, well, we tried. We'll keep doing these, keep trying to work your way through it. It just comes down to practice. Chapter 17 is addition to polar pi bonds. Okay, so I talked way too much on topics I didn't want to talk about. General breakdown set up here. Really, it's not as bad as it looks. We've got a whole bunch of nucleophiles. We just add them to carbonyls. That's all that's happening in Chapter 17. And we add them in sometimes interesting ways. So, ketones and aldehydes, super, super relevant. For those of you moving into biochemistry, pharmacy, any of those kind of concepts or Cs, ketones and aldehydes are of critical importance. Ultimately, the carbonyl functional group itself is stupidly important. Everything that happens in biochem comes back to a ketone or an aldehyde. Okay? Really, really, really important. So pay attention to these. They do show up again and again and again. Nomenclature. Oh man, I always forget I put these stupid slides in. We'll come back to nomenclature. We'll end with that. Where's the chemistry on the carbonyl? Okay. We've got the carbon. What about the carbon? It's an electrophile. What else do we have? Nucleophile on our oxygen. It's a nucleophile. It can also be... What else do we have? Our alpha position is acidic. Okay. Believe it or not, we've already looked at the basic characteristics of the carbonyl oxygen. We've also addressed the acidic functionalities of our alpha position. What we haven't looked at yet is the electrophilic character of the carbonyl. Why is it electrophilic? Why is it partially positive? Because isn't quite right. It's attached to an electronegative oxygen, drawing that electron density away. There is a polar bond, a polar weak bond attached to that oxygen where the electrons are being shifted the other direction. So when we're looking at this, Chapter 17 addresses strong nucleophiles. So really what we're centering on is that electrophilic characteristic of the carbon. Okay? In Chapter 17, it's all about the wickedly strong nucleophiles. Hydride, carbon, which is an interesting one. Carbon's not easy to become a nucleophile. You can see this in the form of the Grignard reaction. You can also see it with acetylides, which you've already seen. And the other big named reaction is the Wittig reaction. Okay. The last carbon nucleophile, which is officially not a strong nucleophile, is the Gilman reagent, which really should be classified under the weak nucleophile subcategory, but that's how they decided to organize it. Okay. Chapter 18 moves to your weak nucleophiles. Oxygen, nitrogen, nitriles, and your enolates are all considered weak nucleophiles. Okay. So all we're trying to do is look at those kind of nucleophiles and how they react with a carbonyl and what things we should be considering within it. So if we take a look at a general reaction, we start with a carbonyl. There's a nucleophile. Which is it? Strong or weak? How do you know it's strong? It's negatively charged. Okay, so that's a big tip-off. Doesn't always work, but we'll address that when we cross that bridge. What's the very first thing that we would expect to happen? The nucleophile attacks the carbon of our carbonyl, which then means the carbon has too many bonds. So what do we have to do? Break a bond, and we'll push those electrons onto the oxygen. And whoa, shoot, that worked. So our nucleophile is now attached. Okay. That negatively charged oxygen now has nothing else to react with. The oxygen, as a negative charge, believe it or not, is not a strong enough nucleophile to attack another carbonyl to continue this reaction. So it stalls right there. Since it is negatively charged and it can't propagate any further, what we're going to have to do is now add something to the reaction to neutralize it. This is our workup phase. What do we need to stabilize a negative charge? Positive. What's our best source of positive?
Acid.
An acid. So we can now add an acid. What happens in our last step? Don't all shout it out at once. We get the acid-base reaction of the negative oxygen sharing with that positive hydrogen, and we have our result. Did we have to go in this order? It's a tricky question. What if I started with H+? What would that H+ do?
It would stabilize the negative charge on them.
We would take the electrons from our carbonyl of our oxygen, react with the H+, which then gives us our protonated state and our now positive carbon, our carbocation. Under these conditions, you'll find that we still have a nucleophile. But what is this nucleophile? It's a weak nucleophile. Why is it weak? No charge. The nucleophile can then go through an attack, form our new bond, and we'd have this structure. What's the problem with this structure? It's charged. So what could we do? That nucleophile is usually electronegative enough that it will suck the electrons right away from that hydrogen, and that's all we would end up showing. We'd end up with our final product. Okay. What is picking up that hydrogen? Anything remotely basic in solution, say like another weak nucleophile floating by. Okay? The details of that aren't important. So where we will pick up on Wednesday is looking at these quick examples of nomenclature. Yes, I will turn it into a quiz, and I will give you 2 minutes to complete that quiz. So it may not be a bad idea to go through and already do that ahead of time. Just saying.